In exercise 13.19, we are taking alcohols, things that have OHs on them, and we're turning them into alkyl halides. So those are carbon chains that have a halogen on them. Remember, the halogens are all of the elements in group 7A on the right side of the periodic table. So that's fluorine, chlorine, bromine, or iodine. And for this exercise, we're really going to focus on chlorine and bromine. Those are kind of the ones that are intermediate in size. Remember, atoms get bigger as you go down and to the left on the periodic table. So fluorine, which is at the top, is really small. Iodine, which is at the bottom of group 7A, is really large. So those have kind of unique behaviors because of their unique sizes. Chlorine and bromine are in the middle of the range, and so they will have a similar type of behavior, and they're usually the ones that are used as leaving groups in organic chemistry because they don't leave too easily, but they aren't too hard to get to leave. The fluorine is really hard to get to leave because it's so small, it's unable to dilute a negative charge over its volume very well. And an iodine leaves really easily because it's so big. It dilutes negative charge so well and stabilizes itself a lot. And so the fluorine and the iodine, which are sort of at the extreme opposites of the spectrum, are not going to be the alkyl halides that we really focus on in this class. You'll see over and over again, we usually focus on bromine and chlorine. So here, when we say we're going to turn an alcohol into an alkyl halide, what we're really talking about is replacing an OH with either a Br or a Cl. Okay. Now let's talk a little bit about the background for this. I think once we talk about the background, you'll see that solving these exercises is not so bad. But just to make sense of everything and to help everything become more memorable and rational, let's talk about some background. So if we're replacing an OH with a halogen, that means we're substituting a halogen, an OH for a halogen. Right? We're doing a substitution reaction. And so there are going to be two ways we can do this. We can do an SN1 reaction, or we can do an SN2 reaction. And the way that we go about these is going to be slightly different. For an SN1 reaction, you'll know that you have to do an SN1 reaction if you have a tertiary alcohol. So a tertiary alcohol. That's the sign that you have to use the reagents for an SN1 reaction. Now, a tertiary alcohol, that's where you look at the alcohol, look at the carbon that's bonded to it, how many other carbons is that bonded to? If it's 1, 2, 3, then that is tertiary. And that means that you're going to want to do an SN1 reaction. So look at the carbon that the OH is bonded to, ask yourself how many carbons is that bonded to? If it's bonded to 1, 2, 3, then you know you'll want to use the reagents to do an SN1 reaction. Now, the reagents for adding a Br, well, let's do an HCl first, a Cl for replacing this group with an HCl. With a Cl. So the reagent for that is HCl, hydrogen chloride. If you wanted to replace this OH with a Br, and the OH is on a tertiary carbon, then, so if you wanted to do this, you wanted to do an SN1 reaction, take a tertiary alcohol and replace the OH with a Br, the reagents you would use for that would be HBr. So let's just quickly walk through. The mechanism for these two is really the same. You can see that the reagents are really similar. You're just replacing a bromine with a chlorine, and you accomplish the same transformation. Let me just walk through an example of how that would work. Let's do this with a chlorine, but the bromine, the mechanism for that would be exactly the same. So we'll take this. Now, if you ever have to guess a mechanism, or if you ever don't remember one, and you want to think through it, what you really want to do are look for the positive and negative charges on each of the molecules. 95% of organic chemistry is just opposite charges attracting. So if you look for the charges on this molecule on the left, the oxygen is very electronegative, so it becomes slightly negative. It pulls electrons away from the hydrogen, which becomes slightly positive, and also this carbon, which becomes slightly positive. Chlorine, and the other molecule, is also really electronegative. It's sort of at the top right of the periodic table. Remember, electronegativity increases as you go up and to the right. So this chlorine will pull electrons to itself, become slightly negative, and the hydrogen will become slightly positive. So when you look at these two molecules and you're trying to think about how they're going to interact, you're thinking about how these opposite charges can connect with each other. Now this oxygen and this alcohol, which has a slightly negative charge, is going to be very attracted to the slightly positive charge on the hydrogen there. We know that chlorine is a really good leaving group. We saw that a bunch in Organic Chemistry 1. The reason was because it's so big, so it can take electrons, have a full negative charge, and just spread it out, dilute it over its enormous space. That stabilizes it, and so it can take those electrons and leave, and be stable that way. So, in other words, it's a good leaving group. All it needs is a little push, and the push comes from this oxygen slapping into this molecule, sticking to the hydrogen, and kicking those other electrons off. So the first step in this sort of SN1 mechanism is to take that alcohol, this lone pair is going to become a bond now, a bond to that hydrogen that it attacked, and the chlorine will be off living its best life with a full negative charge. Now this oxygen here will have a full positive charge. It has 3 bonds. It's a pattern you'll see over and over again. When oxygen has 3 bonds, it has a full positive charge, but you can pause the video and calculate the formal charge just to make sure if you don't feel comfortable with that yet. Remember, it's the group A number that it's in minus the dots plus the lines around the atom. That gives you the formal charge. Okay, well, what we've done after this first step is we've taken a group that was a terrible leaving group, and we've turned it into an awesome leaving group, right? After this proton transfer here, we have turned this into water. If that leaves, that's water, right? If this left before, it would be OH minus. That's really unstable. You would remember that from Organic Chemistry 1 as a strong base and a strong nucleophile. And it's very reactive in both of those contexts because it's so unstable. So that, if it were unstable and it tried to leave, it would just snap right back on the molecule. But if this leaves, as it's jostling around in the container, as these bonds are vibrating 10 trillion times a second, and it's smacking into molecules on every side, hundreds of trillions of them, and the sides of the beaker, as it does that, if this slips off of the molecule, gets smacked off of the molecule, then it's not OH minus, it's water. And water is really stable. And so, in other words, it leaves the molecule and is stable. That makes it a good leaving group. So if it takes these electrons, that becomes the second lone pair here. That means this carbon is now missing a lone pair. It's a carbocation. And so this water here functioned as a great leaving group. So this water became a good leaving group. Now at this point, after we have the loss of that leaving group here, we have water jostling around, stable, and we have this chlorine. Now the full negative charge on the chlorine feels the full positive charge on this carbon. When it comes close to it, the chlorine's so big, it can accommodate a lot of electrons. The electrons all swarm to one side of the atom to get close to this positive charge. That gives that side of the atom an especially negative charge. And what ends up happening is the chlorine can act as a nucleophile and attack that carbon. So that you end up with the chlorine attached to that carbon. So notice, here you had 1, 2, 3, 4 carbons total. Here you have 1, 2, 3, 4 carbons total. You just have the chlorine attached to it. So notice what happened overall here. We did a proton transfer to turn the OH into a better leaving group. Then we had loss of a leaving group. That gave us a strong electrophile, carbon with a full positive charge that the nucleophilic chlorine could attack. So we had nucleophilic attack, and the overall change is that the OH was replaced by a Cl. Now, if you were going to draw this mechanism for, and so that explains this top one. If you were to draw the mechanism for the next one down, it's the same exact thing, just anywhere you have a Cl, write a Br. And the reaction is exactly the same. So this is an SN1 reaction. You can do an SN1 reaction to replace the OH of an alcohol with a halogen, either a chlorine or a bromine, by adding these strong acids, HCl or HBr. And you'll know to add those specific reagents because the OH that you want to replace will be on a carbon that's bonded to 3 other carbons. In other words, it will be a tertiary alcohol. That carbon that has the OH on it is bonded to 1, 2, 3 other carbons. Okay, we said there are 2 ways. Our goal here is to learn how to replace OHs with Cls or Brs, to substitute the OH for with a Cl or a Br. And that's a substitution reaction. There are 2 ways to do a substitution reaction. We just saw the SN1 way. Now let's look at the SN2 way. Now for an SN2 reaction, you'll know to use these reagents because the alcohol will be primary. If the alcohol is secondary, really the fastest reaction is to do an SN2 reaction, but technically either would work. But really, if it's secondary, I would encourage you to do the SN2 reaction, just because it'll be faster. Okay, so if the carbon that has the OH on it is just bonded to 1 other carbon, then it's a primary alcohol, and you would want to use the reagents for an SN2 reaction. Again, if the carbon that has the OH on it is bonded to just 1 other carbon, then it's a primary alcohol, and you would want to use the reagents to accomplish an SN2 reaction. So in this case, let's say we had ethanol. This is drinking alcohol here, and we wanted to make ethyl chloride, so replace the OH in ethanol with a Cl, or ethyl bromide. So we want to replace the OH in drinking alcohol, ethanol, with a Br. What reagents would you use then? So these reagents are going to look a little funny, but they will come back regularly throughout the semester. They're sort of like guest stars, repeating guest stars that'll show up every few episodes, but they're not in every single chapter. They will be important for this test, of course. Okay, first I'm going to list the reagents, and then we'll walk through the mechanisms for how they work. If you want to replace a primary OH, primary alcohol, with a Cl, the reagents you want to use are thionyl chloride, SOCl2, and pyridine. Now, like I said, we're going to unpack all of that in just a second, but I'm just introducing it right now. If you want to replace a primary alcohol, an OH on a carbon bonded to just 1 other carbon, with a Br, then you'll want to add something called phosphorous tribromide, PBr3. Okay, let's look at the mechanisms for each of these one at a time. First, replacing an OH with a Cl using thionyl chloride and pyridine. Now, the idea behind this is really similar to the idea behind the SN1 mechanism, and that's one of the beautiful things about taking the extra time to understand these mechanisms. At first, it's an investment. It definitely takes time, but what you'll see are conceptual connections that simplify and boil down the things that you need to memorize. So they're not just foreign things that are separate and disconnected. They're all kind of unified through a very small number of concepts. What we saw in the SN1 reaction is, in order to replace the OH with the Cl, the OH had to leave, and the Cl had to come in. So loss of a leaving group and nucleophilic attack. But OH is a bad leaving group, so we had to turn it into a better leaving group. In an SN1 reaction, we did that with a proton transfer. We turned it into water. Well, this thionyl chloride, this SOCl2 with pyridine, that is going to act to turn this OH, which is a bad leaving group, into a good leaving group. So thionyl chloride looks a little bit like this. You've got sulfur double bonded to oxygen, so it's like the sulfur version of a carbonyl, with a chlorine on each side. Okay, now oxygen is very electronegative, pulls electrons to itself, becomes slightly negative. Chlorine is very electronegative, pulls electrons to itself, becomes slightly negative. The sulfur is bleeding electrons on every side. It's losing electrons to every atom it's bonded to, so it is very slightly positive. The oxygen in the alcohol, and there are two lone pairs there, the oxygen in that alcohol is very electronegative, pulls electrons to itself, becomes slightly negative. And notice again, when we're trying to figure out how atoms react, what we do is we look for the charges. 95% of organic chemistry is just opposite charges attracting. So this negative oxygen here can swoop in and attack that really slightly positive sulfur. The weakest bond will break, as we've seen already in the case of aldehydes and ketones being attacked by sodium borohydride, lithium aluminum hydride, and Grignard reagents. The weakest type of bond is a pi bond. That's the first bond you ever form between two atoms is a sigma bond. Every bond after that is a pi bond. And so this pi bond, which is the weakest bond, will break. And if you're not familiar with why, or you want to review about what those are and the specific differences and how you can recognize them, I strongly encourage you to watch the video I've uploaded for that on the review playlist for the Organic Chemistry 2 class. The first playlist is a review of Organic Chemistry 1, and they talk about the difference between sigma and pi bonds and why one is weaker than the other, why pi bonds are weaker than sigma bonds. Okay, so after that first step, and this is nucleophilic attack, after that first step, what we have is our two carbons. We still have one lone pair here. The other lone pair has gone to form a bond to this sulfur. You still have two chlorines there. Now you just have one bond to this other oxygen. One bond to that other oxygen, and this oxygen here has three bonds and so a full positive charge. So you have a sort of tetrahedral intermediate. This sulfur was trigonoplanar, now it is tetrahedral. And we're not done yet because this is very unstable in a couple places, so it's an intermediate, so this is called a tetrahedral intermediate. Okay, this is where the pyridine comes in. That py stands for a 6-atom ring, where one of the atoms is a nitrogen. So this is py called pyridine. Ends up being a really crucial structure. It appears in a lot of different things, including in biological rings. So a 6-membered ring with what look like alternating single and double bonds. And that nitrogen will have a lone pair on it. So that's pyridine, that's this py. Now nitrogen can act as a base. Even since general chemistry 2, that nitrogen has been the poster child for a Bronsted-Lowry base because it has this lone pair that can accept an H+. And that's exactly what it does. This nitrogen is slightly negative, but these electrons are exposed to the outside world, so when they feel this slightly positive hydrogen here, and notice that that hydrogen is very slightly positive, it's losing electron density to the oxygen because of the oxygen's electronegativity first. But the oxygen also has a full positive charge that really pulls the electrons towards it. So this hydrogen is really slightly positive. So what can happen is the lone pair on that nitrogen can act like a Bronsted-Lowry base, attack the hydrogen, kick the electrons there, and we've sort of stabilized this molecule. So what we have after that proton transfer is this ion. This is when nitrogen has 4 bonds. You'll recognize it as an imium ion. This is a pyridinium ion. This was pyridine. This is pyridinium. And the hydrogen would have left here, so now this oxygen would have no charge. Okay. Now, what often happens here, even sometimes this will happen even before this, but what often happens is this oxygen can swoop back down and kick one of the chlorines off. So this tetrahedral intermediate, these electrons can swoop down, kick the chlorines off. And you can see that because the oxygen is negative, and so it's very unstable. So we get that sort of loss of a leaving group there. And now we're in a position where we can appreciate what we've accomplished. We can sort of stand back, look at what we've accomplished here so far. So this lone pair will go in between there. That chlorine will leave. Okay. So what have we accomplished here? We've turned this bad leaving group, the OH, into a good leaving group. This whole thing is a good leaving group. What can happen now is this chlorine that left before, a second ago, that chlorine can swoop in, attack this carbon, kick that oxygen off, and really just do an SN2 reaction. So now you'll notice the chlorine will be bonded to that carbon, and you will have this oxygen with a full negative charge on it. And now you can see why this was a good leaving group. Because this oxygen, the lone pair here, is allylic to this pi bond. It's one atom away from an atom in a pi bond. And so that can exist in a p orbital that's parallel with the p orbitals here. And so the electrons can spread out over all three of those atoms. When you spread charge out, you stabilize it, you dilute it in space. Now, if that doesn't sound familiar, having an allylic lone pair, I strongly encourage you to go back and watch the video on resonance and the first resonance pattern, the allylic lone pair. And you can see how that resonance pattern shows you how the charge and the electrons in an allylic lone pair spread out over multiple atoms and stabilize themselves. So that overall, in this mechanism, what we've done is we took the OH and we replaced it with a Cl. The way we did it was we treated it with thionyl chloride, and thionyl chloride really turned the OH into a good leaving group. And once we did that, we just did an SN2 reaction with one of the chlorines in thionyl chloride. And the pyridine was there just to stabilize this intermediate, to stabilize that there. Okay, so much for thionyl chloride. Hopefully that clarifies how you can use thionyl chloride and pyridine to turn a primary alcohol into a primary alkyl chloride. Now let's just quickly walk through the mechanism for how phosphorous tribromide works, and you'll be able to see how we can apply this to the exercises in this next exercise. So let's take this reaction, and we'll walk through the mechanism for how this works. Okay, so phosphorous tribromide looks like this. You'll see the concept is really similar to the SN1 reactions and the SN2 reactions. Our goal is to turn this bad leaving group into a good leaving group. We're trying to replace it or substitute it with the Br. So this needs to leave, the Br needs to come in. So we have to turn that bad leaving group into a good leaving group. Notice how many electronegative elements we have bonded to the phosphorus. Each one of those bromines pulls electron density to itself, becomes slightly negative. And the phosphorus loses that electron density, becomes slightly positive. That oxygen in the alcohol, as we've seen before, pulls electron density to itself, becomes slightly negative. And the hydrogen and the carbon bonded to it lose that electron density, becomes slightly positive. The oxygen can swoop in, attack the phosphorus, kick one of the bromines off, and really just do an SN2 reaction. And what we have happen there is the alcohol, this oxygen, will have a hydrogen on it, and the phosphorus that's still bonded to two of the bromines. The other bromine will be floating around in solution with a full negative charge. All right? So this bromine took those electrons, became this bromide ion. The phosphorus with the other two bromines attached to this oxygen. Now notice that oxygen has 3 bonds, so it has a full positive charge. And so what we've done is we turned this OH, which was a bad leaving group, into a good leaving group. This whole thing is a great leaving group. Because if it steals these electrons, if it takes them, that will just stabilize this positive charge. So the bromine that left can come back in and do an SN2 reaction, attack the carbon, kick that leaving group off, and you're left with the bromine there, and floating around in solution, you'll still have that oxygen with the hydrogen on it, bonded to a phosphorus that has 2 bromines attached. So notice, what PBr3, what phosphorus tribromide accomplishes is it replaces the OH with a Br. It does that by being bonded to 3 electronegative elements, so the phosphorus is a great electrophile. It tempts this oxygen into attacking it. That's an SN2 reaction that kicks one of the bromines off. That bromine comes back around and does another SN2 reaction to kick this good leaving group off. Okay, so overall, big take-home story is, if you're doing an SN1 reaction and you want to replace an OH with a Cl, you use HCl. If you want to replace the OH with a Br, you use HBr. And you'll know to do that because the OH will be on a carbon that's bonded to 3 other carbons. If you're doing an SN2 reaction and you want to replace the OH with a Cl, you use thionyl chloride and pyridine. If you want to replace it with a Br, you use phosphorous tribromide. And you'll know to use these reactions because the OH will be on a carbon bonded to just 1 other carbon. One last thing about these SN2 reactions that you might remember from Organic Chemistry 1 is that when you do an SN2 reaction, you get inversion of configuration. So when the nucleophile attacks, it flips the other 3 reagents, right? Those 3 white balls there, those hydrogens, were pointing sort of to the left after that red nucleophile attacked and kicked the green leaving group off. They're pointing toward the right in the opposite direction. So if that was a chiral center, it would flip configuration. There's always backside attack in SN2 reactions. Whatever side the leaving group is facing, so like the green one was on the right here, the nucleophile will attack on the opposite side, so the red one attacked on the left here. So if you look at something like our first exercise, the first part of 1319, it says, identify the reagents you would use to accomplish each of the following transformations. In A, you'll notice the bonds went from going towards you to going away. So already we know this is an SN2 reaction because the leaving group, the nucleophile attacked on the opposite side as the leaving group did. So you got inversion of configuration there. That's the technical term for when the nucleophile attacks on the opposite side of where the leaving group is facing. And you kind of did have to know that. You had to recognize that that's a feature of an SN2 reaction here because the carbon that has the OH on it is bonded to 2 other carbons. So you might think that you could do either SN1 or SN2 here, but you have to do SN2 because only SN2 will give you this inversion of configuration all the time. So how do you do an SN2 reaction to replace an OH with a Br? That's phosphorous tribromide, like we saw above. And notice they're not asking for the mechanism here. They just want the sort of recipe. Okay, here. Look at the carbon that has the OH on it. This one here. It's bonded to 1, 2, 3 other carbons. That means it's tertiary. That means that this is going to be an SN1 reaction. How do you replace an OH with a Br in an SN1 reaction? HBr. Right? The OH steals the H from the HBr, turns into a good leaving group. It leaves, you have a trigonal planar intermediate, the bromine swoops in and attacks. Okay, let's try the next one. Here, the carbon that has the OH on it is bonded to 2 other carbons, so it's secondary. So right now we're not really sure whether to do an SN1 or an SN2 reaction. But look at how the bond changes. It goes from being pointing toward us to pointing away all the time. That's inversion of configuration. And so this is going to be an SN2 reaction. So the way you would accomplish that transformation to replace an OH with a Cl with an inversion of configuration, so SN2, is to use thionyl chloride, SOCl2, and pyridine. For D, we see a similar thing. We see the carbon that has the leaving group on it, the OH, the alcohol, is bonded to two other carbons, so it's secondary. But then look at the bond. It goes from facing toward us to facing away. That's inversion of configuration, so we know it's SN2. Replace an OH with a Br in an SN2 reaction. That's phosphorus tribromide, PBr3. How about this one? You look at the carbon that has the OH on it. It's bonded to two other carbons, so it's secondary. Now, there's no chiral center here. We don't see this switching, so we could really use either SN1 or SN2. You can use either. Technically, an SN2 reaction would be faster, but you could use either in this case. So you could either use, in the SN2 reaction, thionyl chloride and pyridine, or you could use HCl. Either of those would accomplish that reaction. The first one through an SN2 mechanism, the second one through an SN1 mechanism. For F, you would look at this carbon that has the OH on it. It's only bonded to one other carbon, so that's primary. That means that this is going to be an SN2 reaction. We're trying to replace an OH with a Br. In an SN2 reaction, the reagents you would add for that is phosphorus tribromide, PBr3. And that is that. So you can see that solving these problems, writing the answers for these problems, is not time-consuming. What takes a little effort is to understand the backstory to these characters, PBr3, SOCl2, and PY. What are they? What are they doing? And you might be tempted at this point not to put in the effort to do that, to just scrub ahead through the video until you see the answers and write those down. But if you do that, you will pay for that later. It's actually, ultimately, by the end of the class, it's more efficient, and you spend less time studying, and you get a better grade if you understand the mechanisms behind these things. That allows you to see connections and to remember things more easily, to see reagents, understand how they'll behave, to see them as characters in stories that are easier to remember. If you just treat them as random things that you're memorizing in order to solve one problem, it'll be very difficult for them to keep you in your memory, for you to keep them in your memory throughout the whole semester. And these reactions will come back in our very last chapter and in many chapters in between. So in 16 weeks, you'll still want to remember this. And if you just memorize it just to answer this one question, you'll see it will come back to haunt you. So if you're putting in the extra effort to understand the mechanisms, you don't have to be able to draw the mechanisms, but just to understand them, to get a sense of what's happening conceptually, it'll really pay off later.